Hello. In the previous lecture, we discussed how we can use being a PID and deduce that my ring is a U of D. So essentially, all together, we have proved that a Euclidean domain implies that the ring is a PID, and a ring being a PID implies that it's a unique factorization domain. We've also seen how we can show certain rings are not unique factorization domains, essentially by showing that certain elements are irreducible but not prime. We can deduce that that particular integral domain is not a unique factorization domain. Now, in today's lecture, we want to show that being a UFD does not imply that the ring is a PID. In fact, we prove a very interesting result that says that ring of polynomials with integer coefficients is a unique factorization domain, but we know that this is not a principal ideal domain. This is not a PID. For instance, you've seen that the ideal generated by 2 and x is not a principal ideal of this ring. Okay, so and this is going to take a good portion of today's lecture to show that the ring of polynomials with integer coefficients is a U of D. The main ingredients of the proof are these three results that we have proved, at least two of them. I mean, in fact, we have proved all three, but we are going to strengthen the third part a bit. So what are the main ingredients? The first one is that the ring of integers is a U of D. We proved this based on the fact that the ring of integers is a PID. It's a Euclidean domain, and therefore it's a PID. The other result is that when I give you a field F, and then a ring of polynomials with coefficients inside F is again a Euclidean domain, and therefore it's a PID, and therefore it's a U of D. And finally, we had proved Gauss's lemma, and Gauss's lemma gives us a connection between elements inside Q bracket X and elements in Z bracket X by looking at the primitive form of a polynomial with rational coefficients and saying that being irreducible in Q bracket X is equivalent to saying that the primitive form of the polynomial is irreducible in Z bracket X. So we have a kind of map from Q bracket X to Z bracket X that sends irreducible elements to irreducible elements, at least among primitive polynomials. Okay, so these are the three important ingredients of the theorem, of the proof of the theorem. So the way that we go about it is like this, that we have these three rings. The ring of integers is a subring of the ring of integer polynomials, and ring of integer polynomials is a subring of ring of polynomials with rational coefficients. And for each one of these rings, we can talk about irreducibility within the smaller ring and within the larger ring. And we will explore the connection between such irreducibilities, or being a prime inside the smaller ring and being a prime inside the larger ring. So for instance, we will show that if an element is an integer element, then this element being irreducible in Z is equivalent to saying that it is irreducible in Z bracket X, or this element being prime in Z is equivalent to saying that it is prime in Z bracket X. Between Z bracket X and Q bracket X, we don't have such a connection, but as I've pointed out in part 3, we give a connection between irreducibility and primeness of elements inside Z bracket X when we view them as an element in Q bracket X. Okay, let's start the proof. We start with understanding integer numbers when we view them as constant polynomials. So the first result that we show is that when I give you an integer, then this integer is irreducible as an element of the ring of integers if and only if it is irreducible as an element of integer polynomials. We do the same by showing, I mean, the property of being prime stays the same. So C is prime as an integer precisely when it is a prime element of the ring of integer polynomials. So these two concepts, they do not change as I pass from Z to Z bracket X. Okay, let's see why this is the case. Let's start with the proof of part 1. This is an if and only if statement, so I need to go from left to right and from right to left. Let's start by showing that the left part implies the right part. So that means I'm assuming C is irreducible in the ring of integers. And then in particular, that implies that C is not 0 and C is not a unit inside the ring of integers. But one thing that we know is that when D is an integral domain, then the group of units of ring of polynomials with coefficients inside D is equal to the group of units of D. So that means being a unit inside the ring of integers is the same as being a unit inside the ring of integer polynomials. So we get this equality. In particular, because C is irreducible inside Z, it's not a unit inside the ring of integer polynomials. Now we go to the more important part of being irreducible, meaning I write C as a product of two polynomials with integer coefficients. Now I need to show that one of them is a unit. So as usual, we start with comparing the degrees of both sides. The degree of C, because C is a constant polynomial and it's not 0, the degree is 0 because C is not the 0 polynomial, but it's a constant polynomial. And degree of product is summation of degrees. So 0 is the same as degree of F plus degree of G, but that means that both F and G are non-zero constants. So both of them have degree 0. So both of them are non-zero constants. So if I write them as A and B, so these are integer numbers. So suppose F is A and G is B, both of them are non-zero integer numbers. Then knowing that C is A times B and knowing that C is irreducible in Z, we deduce that either A is a unit or B is a unit in the ring of integers. But as we've mentioned over here, the group of units of Z, or D in general for any integral domain, is the same as the group of units of the ring of polynomials with coefficients in Z or D in general. So these are the same. So that means either A is a unit or B is a unit, and that's exactly what we wanted to show. So this implies that C is irreducible in the ring of polynomials with integer coefficients. Okay, so now let's go from right to left. So this time we assume that C is irreducible in the ring of integer polynomials, and we want to deduce that it is in fact an irreducible element of the ring of integers. The first thing that we observe is that C is not 0 and it's not a unit of the ring of integers. So we go to the more interesting part, meaning we assume that C is written as a product of two integers, A and B, and we view A and B as two non-constant polynomials. Because C is irreducible as an integer polynomial, we deduce that either A is a unit in the ring of integer polynomials or B is a unit in the ring of integer polynomials. But again, because Z is an integral domain, the units of this ring of polynomials is the same as the units of Z. And that means either A is a unit or B is a unit, which implies that C is irreducible in the ring of integers. So irreducibility of an integer number doesn't change as I enlarge my ring. So you see, this doesn't happen when I make it a bit larger and go to Q bracket X. In that case, all non-zero integers are units. So all of a sudden they are not irreducible anymore. So 2 is irreducible in Z, but 2 is not irreducible in Q bracket X. But what we just showed is that 2 is still irreducible in Z bracket X. Okay, Now let's go to the next part where we want to show that being prime doesn't change as we go to the larger ring of integers with ring of polynomials with integer coefficients. So again, it's an if and only if statement. We have to go from left to right and right to left. With a similar argument, we can deduce that C is not 0 and C is not a unit. So we immediately go to the more important part, which means that we assume C divides product of two integer polynomials, and I have to show that it divides one of them. But what does it mean that it divides this in Z bracket X? It means that I can find an element of Z bracket X such that the product of F and G is C times H of X. Now our main tool is Gauss's lemma and using the content of both sides. So content of the left-hand side is absolute value of C times content of H, and this is supposed to be content of F times content of G. So that means that C, you see all of these numbers are integer numbers. So this is inside Z. So that implies that C divides product of the contents of F and G. But remember, C is prime. C is a prime integer. So that means when it divides product of two integers, so this is an integer, this is also an integer. Because C is prime in the ring of integers, when it divides product of two integers, it should divide one of them. So that means C divides either C divides the content of F or it divides the content of G. But remember, content of F divides F in Z bracket X. Essentially, here we have that polynomial F is its content times its primitive form, and primitive form is an integer polynomial. And the same is true for G. So that means that F is divisible by the content of F and so on. So that implies that C divides the polynomial F or C divides the polynomial G in the ring of integer polynomials. And that's exactly what we wanted to show. This implies that then again, if C divides product of two integer polynomials, it should divide one of them. Therefore, C is prime in the ring of integers, in the ring of polynomials with integer coefficients. Now we want to go the other way around. So we assume that C is an integer, which happens to be prime in the ring of integer polynomials. So again, it cannot be 0 or it cannot be a unit in the ring of integers. So we focus on the more interesting part, meaning we assume that C divides product of two integers. I have to show that it divides one of them. Again, we view these A and B as constant polynomials, and we use the fact that C is a prime number in a prime polynomial, a prime in the ring of integer polynomials. That means that C should divide A in the ring of integer polynomials, or C should divide B in the ring of integer polynomials. This means that I can find some integer polynomial F such that when I multiply C by this polynomial, I end up getting A, or when I multiply by C, I end up getting B. Again, comparing the degrees of both sides, we deduce that degree of F should be 0, and from here we deduce that it is indeed an integer. So that means that either A is an integer multiple of C, or B is an integer multiple of C, which means either C divides A in the ring of integers, or C divides B in the ring of integers, which is equivalent to saying that C is prime in the ring of integers. So altogether, we deduced that when I enlarge my ring from the ring of integers to the ring of integers, integer polynomials, I don't change the properties of being irreducible or being a prime number. Okay, so these two properties do not change after enlarging the ring of integers to the ring of integer polynomials. Now, let's recall what is a primitive form of a polynomial. Whenever I give you a rational polynomial, which is not zero, we defined its content, and we showed that this content can be defined in a unique way so that the content is non-negative. The content is a positive rational number, and when I divide my polynomial by this positive rational number, I end up getting a primitive polynomial. And the pair of alpha of f and f bar is unique. So therefore, we get a function from non-zero polynomials to non-zero integer polynomials. So from ring of polynomials with rational coefficients to the ring of polynomials with integer coefficients, essentially sending f to the primitive form of f that I often denote by f bar in today's lecture. Now, Gauss's lemma tells me that these contents, the content function is multiplicative, which in turn implies that this primitive part is multiplicative, meaning that when I look at product of f and g and then look at its primitive form, it is like looking at the primitive form of f and multiplying it by the primitive form of g. Remember, we have this result that content of fg is content of f times content of g, and f times g is its content times fg bar, the primitive form of this. But at the same time, it is equal to content of f times content of g times f bar times g bar. So these two cancel out, and we end up getting that the primitive form of f times g is product of the primitive forms of f and g. So it's quite interesting because now we are getting a map that preserves the multiplication between non-zero polynomials with rational coefficients and non-zero polynomials with integer coefficients, with this extra property that the image of this map consists of primitive polynomials. Now we've proved many interesting results about this, and I'm going to add to that list and recall some of the results that we have already proved. So this primitive part, the primitive form of polynomial, satisfies many multiplicative properties of the function f, of the polynomial f. So let's record some of these properties. So the first thing is that whenever I give you a polynomial with rational coefficients, it is a unit in this ring if and only if its primitive form is a unit in zx cross. Some of these statements I formulated in this way, and instead of writing, we know that the group of units of z bracket x is just plus minus 1, but I write it in this form on purpose because later we are going to generalize these statements for an arbitrary u of t instead of z. So it's better to have the statements like this, which are true, which will be true, I mean, these statements that are written like this are true when I replace z with a u of t. Okay, so this is one of the statements, that sending a polynomial f to the primitive form of this does not change the property of being a unit. But of course, I mean, within different rings. Another thing is that if a polynomial f divides g in this larger ring, this property is equivalent to saying that the primitive form of f divides the primitive form of g in the smaller ring, ring of integer polynomials. Irreducibility is preserved under this map, so but in different fields. So f is irreducible in Q bracket x if and only if its primitive form is irreducible in Z bracket x. Being prime is the same. So f is prime in Q bracket x if and only if its primitive form is prime in Z bracket x. So you see many interesting properties are preserved under this primitive map. And notice that all of these properties are kind of about the multiplicative structure of these two rings. And the main reason that we can deduce most of them is because the primitive map is a multiplicative map. Okay, so let's see why we have this. Essentially, all of these results are based on Gauss's lemma and the fact that the primitive map is multiplicative. And all of these results are if and only if. So for most of these steps, I need to go from left to right and right to left. In some of them, I can deduce both directions immediately. But let's start with part one. I want to deduce that f is a unit in Q bracket x if and only if its primitive form is a unit in Z bracket x. But what does it mean that it's a unit in Q bracket x? We know that the group of units of D bracket x for any integral domain is the same as the group of units of D. When D is a field, then it's equivalent to saying that f is a non-zero polynomial. When f is a non-zero constant polynomial, f is a non-zero constant polynomial. So in that case, the content is just absolute value of f. So the content of f is just its absolute value. Again, notice that here, because f is constant, f is a non-zero constant polynomial. Then the content is just absolute value of a, which means that the polynomial itself is plus minus the content. So that means the primitive form of f is just plus minus 1. So that means that we get that f bar is a unit. So when we are working with some other integral domain, we need to still formulate properly what do we mean by the content of the polynomial. And when we do so, we will see that it will be equivalent to saying that the primitive form is a unit inside the unique factorization domain D that's given to us. But for now, let's focus on Z and not get confused with other things. Okay, this shows part one. Let's go to part two. So this time I'm going to assume that f and g are two polynomials with rational coefficients, and g is a multiple of f inside this ring. That means what? I can find some polynomial with rational coefficients and write down g as f times h. Now I'm going to apply the primitive function to this. This means the primitive form of g can be written as the product of primitive forms of f and h, which implies immediately that notice that this belongs to Z bracket x. So this implies that g bar, the primitive form of g, is a multiple of the primitive form of f by an element inside Z bracket x. Okay, so we show that when f divides g in Q bracket x, then f bar divides g bar in Z bracket x. Now let's go the other way around. So we are going to assume that f bar divides g bar in z bracket x, which means I can find some integer polynomial and write down g bar as q times f bar. So we can write down g bar as an integer polynomial multiple of f bar. But what is g bar? G bar is, again, it's the primitive form, which means g is its content times g bar. Alternatively, I can say that g bar is the content of g inverse times g. Or, okay, maybe for this one, I can multiply both sides by this. But so instead of g bar, I can write down this, or I can multiply both sides of this by the content of g. And instead of f bar, I can write down the same. I can write down the content of f inverse times f. So using these two equations, I can rewrite this one. And instead of g, I can write, instead of g bar, I'm going to treat it as the content of g times g bar. So I have this content factor on the other side. And instead of f bar, I have content of f inverse times f. And the q is still there. And notice that this is a polynomial with rational coefficients. So all of a sudden, I'm writing g as a multiple of f by a factor inside q bracket x. So f divides g in q bracket x. So now we showed both sides. Now we showed that if I know that f bar divides g bar in z bracket x, then I can deduce that f divides g in q bracket x. Now next I want to show that if f is irreducible in q bracket x, then its primitive form is irreducible in z bracket x and vice versa. Now notice that f is its content times f bar, but the content is a unit inside q. It's a non-zero rational number. So whenever I multiply an element inside some ring by a unit, being irreducible or not doesn't change. So f is irreducible in q bracket x if and only if its primitive form is irreducible in q bracket x. So in fact, in here, we can also argue it like this, that whenever I look at polynomials with coefficients inside a field, this polynomial is irreducible precisely when it cannot be written as a product of a smaller degree polynomials, and this does not change after I multiply it by some scalar, non-zero scalar. Alpha of f is a non-zero constant. So when I multiply f bar by this non-zero constant, I do not change the fact that whether or not f bar is irreducible in q bracket x. So f is irreducible in q bracket x precisely when f bar is irreducible in q bracket x. But long ago, we used Gauss's lemma and showed that if I start with a primitive polynomial, then being irreducible in q bracket x is equivalent to being irreducible in z bracket x. So among primitive polynomials, irreducibility in q bracket x and z bracket x are equivalent. So all of a sudden we deduce that f is irreducible in q bracket x if and only if f bar is irreducible in q bracket x, and that is equivalent to saying that f bar is irreducible in z bracket x, and that's exactly what we wanted to show. So all together, we deduce that being irreducible in q bracket x is equivalent to being f bar being irreducible in z bracket x. Now we go to the last part of the proposition, which says that for f is prime in q bracket x if and only if its primitive form is prime in Z bracket X. So f is, I'm going to assume that f is prime in Q bracket X. I want to show that its primitive form is prime in Z bracket X. Again, it's easy to see that using the parts that we have already proved, it's easy to show that the primitive form of f is not a unit inside the string and it's not zero. So we focus on the interesting part of being prime, meaning I'm going to assume that f bar divides product of two integer polynomials, and I'm going to denote these integer polynomials by h1 and h2. So h1 and h2 are two integer polynomials, and my assumption is that the primitive form of f divides this product. And from here, I want to deduce that f bar, either f bar divides h1 or f bar divides h2. Okay, let's see why we can show this implication. But let's start with what it means that f bar divides this product. It means that I can find some integer polynomial such that f bar times this integer polynomial is h1 times h2. Okay, so f bar times q is h1 times h2. But what is f bar? Again, let's recall the definition of content. F of x, it's its content times f bar. So from here, I can rewrite f bar as its content inverse times f. So that means I can write f bar and say it is f of x times the content inverse, and put the content inverse by q of x. So this means I end up getting a rational polynomial, a polynomial with rational coefficients, and when I multiply it by f, I get h1 times h2. Alternatively, I can say that either f, okay, so now, so this implies f divides h1 times h2 in Q bracket x. But remember, the assumption is that f is prime in Q bracket x. So this means when f divides product of two polynomials in Q bracket x, then it should divide one of them. So either f divides h1 or f divides h2 in the ring Q bracket x. We showed that f divides g is in Q bracket x is equivalent to saying that the primitive form of f divides the primitive form of g in Z bracket x. So using that part 2 of this proposition, I can deduce that either the primitive form of f divides the primitive form of h1, or the primitive form of f divides the primitive form of h2 in the ring Z bracket x. But notice that h1 and h2 are integer polynomials, and therefore hi's are their content inside h times their primitive form, and this is an integer, and therefore the primitive form of hi's divide hi in Z bracket x. So that means either h1 is a multiple of the primitive form of f, or h2 is a multiple of the primitive form of f in the ring Z bracket x. Remember, the assumption was that the primitive form of f divides this product, and the target was to show that the primitive form of f either divides h1 or h2, and that's exactly what we showed right now. So that means altogether we've showed that f bar is prime in Z bracket x. So we used the assumption that f is prime in Q bracket x and deduce that the primitive form of f is prime in z bracket x. Now we want to go the other way around. So we assume that the primitive form of f is prime in z bracket x. Now I want to deduce that f is prime in q bracket x. What does that mean? We are going to assume that f divides product of two binomials with rational coefficients in q bracket x. So this divisibility is in q bracket x. And we want to deduce that f either divides g1 or g2. But again, using part 2, from here, knowing that f divides this product, we can deduce that the primitive form of f divides the primitive form of g1 times g2. And the primitive form of g1 times g2 is the primitive form of g1 times the primitive form of g2. So we get that f bar divides the primitive form of g1 times the primitive form of g2 in z bracket x. Now, the assumption was that f bar is prime in z bracket x. And in this ring, it's dividing product of two elements. So it should divide one of them. So either the primitive form of f divides the primitive form of g1 in z bracket x, or it should divide the primitive form of g2 in z bracket x. Now we again use part 2 of this proposition. It says that primitive form of f divides primitive form of g in z bracket x precisely when f divides g. So this means the first one implies that f should divide g1, and the second one implies that f should divide g2. So altogether we get that either f divides g1 in q bracket x, or f divides g2 in q bracket x. That's exactly what we wanted to show. So we started with the assumption that f divides g1 times g2, and we wanted to show that either f divides g1 or f divides g2 within the ring q bracket x. Okay, so altogether we deduce that f is prime in q bracket x, which finishes proof of this proposition. So again, let's look at the statement of the proposition. This is an important statement. It says that being prime, having divisibility, being irreducible, being prime again, and being a unit. So these things do not change when we pass from q bracket x to z bracket x and change f to its primitive form. So all these properties are hold. And essentially the main ingredient behind this proposition is Gauss's lemma. So we've been using it in different forms. Okay, now let's see how this proposition can help us to show the main theorem that I started with, saying that the ring of integer binomials is a U of t. We'll start by showing the existence part, meaning I want to say that whenever f is a non-zero, non-unit binomial, then I can write it as a product of irreducible elements. First thing that we do is to separate the integer part of it from the binomial part of it, meaning that I'm going to write it as its content, the GCD of the coefficients, times a binomial that is primitive. Now, an integer binomial, an integer number alpha of f, because ring of integers is a U of t, can be written as a product of irreducibles, but irreducible integers. So I can find a bunch of integer irreducibles and write down the content of f as product of these irreducible integers, because ring of integers is a UFD. Or the content is 1. So in either case, I can write it like this with this convention in mind, that if m is 0, if I have no irreducible factor, that means the content is 1. Now, for the primitive part, what can I do? I'm going to look at the primitive polynomial as a polynomial in Q bracket x. Now, Q bracket x is a UFD because it's a PID, it's a Euclidean domain, it's a PID, it's a UFD. Therefore, I can write f bar as a product of irreducible polynomials, but irreducible in Q bracket x. My goal is to replace this with some irreducible polynomials in Z bracket x. My goal here is also to replace this by Z bracket x. This should be replaced by Z bracket x. And this should be replaced by the same thing. So far, I have this irreducibility in different rings. I have to bring them back in Z bracket x, and that is why we had those lemmas and propositions before coming to the proof of this statement. Now, we have that f bar is product of these irreducible elements of Q bracket x. What we do, we look at the primitive part of both sides. Primitive part of f bar is itself, because f bar is primitive. So I end up getting that f bar is product of the primitive forms of Q sub i's. And in the proposition we showed that knowing that Q sub I is irreducible here is equivalent to saying that Q sub I bar is irreducible in Z bracket x. So I did the magic by looking at the primitive form of Qi. I changed Q bracket x to Z bracket x, end up getting some irreducible element of Z bracket x. Now, alpha of f has been written as a product of irreducibles. F bar has been written as product of irreducibles. So altogether, we get that f is product of P sub i's and Q sub I bars. Q sub I bars, we have already discussed that they are irreducible in Z bracket x. So they are in the right ring. And P sub i's are irreducible in Z, but we showed that for constant polynomials, being irreducible in Z is equivalent to saying that they are irreducible in Z bracket x. So all of a sudden, we are writing f as a product of irreducible elements in Z bracket x. So all the factors are irreducible in Z bracket x. This shows the existence part. So every non-zero, non-constant, every non-unit, non-zero integer polynomial can be written as a product of irreducible elements in Z bracket x. And you see the main ingredient coming to the picture, Z being a UFD, Q bracket x being a UFD, and passing from Q bracket x to Z bracket x, which is essentially Gauss's lemma. Now let's go to the uniqueness part. We have already proved that whenever for an integral domain, we do have the existence part. To show the uniqueness part, it's enough to show that every irreducible is prime. So in order to show the uniqueness part is equivalent to saying that every irreducible is prime. So that's why we focus on this. I start with an irreducible element of Z bracket x, and I want to show that it is a prime element of Z bracket x. First thing that I do, I use again the content, write down f as its content, the GCD of its coefficients, times the primitive polynomial f bar. Now, f is irreducible. So this means whenever I write it as product of two elements, one of them should be a unit. In particular, either alpha of f is a unit, and because it's non-negative, it's positive. So either the content is 1 or fx is primitive. I mean, either the content is 1 and therefore fx is primitive, or the primitive form is plus minus 1, and f itself is primitive. What am I saying? So, and yeah, so either, so again, let's, I've got distracted. So either this factor is a unit or this factor is a unit. So this factor is a unit means that f is primitive, and this factor is a unit means that my polynomial is a non-zero integer. It's constant. Now we consider these two cases separately. Let's start with the case when my polynomial is primitive. So in that case, we know that okay, by assumption, f is irreducible in z bracket x, and it is primitive. But then we showed for primitive polynomials, being irreducible in z bracket x is equivalent to being irreducible in q bracket x. But q bracket x is a UFD, so an irreducible element is prime. So f is prime in q bracket x. But again, in the proposition we showed, a polynomial is prime in q bracket x is equivalent to saying that its primitive form is prime in z bracket x. But f itself is primitive, so its primitive form is itself. So therefore, f being prime in q bracket x together with the fact that f is primitive implies that f is prime in z bracket x. So we showed that an irreducible element of z bracket x when it is primitive implies that it is prime in z bracket x. Now let's go to the second case. In the second case, f is a constant polynomial. Now, if I tell you a constant polynomial is irreducible in z bracket x, we show that that implies it is irreducible in z. Again, ring of integers is a unique factorization domain. So every irreducible element is prime. So A is prime in Z. But being prime in Z for a constant polynomial implies that it is prime in the ring of integer polynomials. That's the lemma that we showed. So altogether, we deduce that a constant polynomial is irreducible implies that this constant polynomial is prime in Z bracket X. And these were the only two possibilities for an irreducible polynomial. So altogether, we deduce that in Z bracket X, irreducible implies prime, and that gives us the uniqueness part of being a UFD. As I've mentioned throughout the proof, at some points in the proof, this theorem itself is a special case of the following theorem that says if D is a UFD, then D bracket X is a UFD. So being a UFD passes to the ring of polynomials with the same coefficient. And when we go through the proof of this special case of Z bracket X, we see that it has three main ingredients. One of them was that Z is a UFD. Here we have that for free. The second was that Q bracket X is a UFD. What is Q? Q is indeed the field of fractions of my integral domain Z. So that's the field that we have to consider, the field of fractions of D. And then I look at Q of D bracket X. And that is the U of D, because again, this is a field. This one is a field. And we showed that when I start with a field F and I look at F bracket X, I get a PID, and therefore it is a unique factorization domain. So the first two ingredients we have for free. What remains is Gauss's lemma. So if we show Gauss's lemma, and then we can deduce the proposition that we had before the proof of this theorem. And based on that, we can prove this theorem that if D is a U of D, then D bracket X is a U of D. So we need to see why Gauss's lemma is true within the context of unique factorization domains. What was Gauss's lemma? So Gauss's lemma was about the content of a binomial, and we need to define content of binomials with coefficients inside a unique factorization domain, or a bit more general, field of fractions of a unique factorization domain. The way that we define content of an integer polynomial was by taking the GCD of the coefficients, and that was the content of a non-zero integer polynomial. So we need to be able to talk about greatest common divisor of a bunch of elements of a unique factorization domain. We start with that. We start by defining the GCD a bunch of elements in a unique factorization domain. Okay, what do we expect out of it? So it should be a common divisor, and in some sense, it should be the greatest one. But in what sense? So we are looking for some element D inside this ring, which is a common divisor of A sub i's. And if you give me any other common divisor, then this other common divisor should be also a divisor of D. So you see, in some sense, I'm using this partial ordering of divisibility, and I'm saying that with this partial ordering of divisibility, this common divisor is one of the largest. But here I do not have the largest. So I don't have the greatest common divisor. I might have multiple choice for those. Indeed, if D1 and D2, both of them, satisfy these two properties, then one of them is a unit multiple of the other one. Okay, so we will continue the discussion of greatest common divisor and valuation maps in the next lecture.